Today we're going to be talking about Charles' law, which says that volume 1 over temperature 1 equals volume 2 over temperature 2. In other words, as the temperature increases, the volume will also increase, or as the temperature decreases, the volume decreases as well. So today we're going to show that using a balloon, and to measure the balloon we're going to use a piece of string. So we're going to start by blowing the balloon up to about a half liter of air. And then we're going to use this string to measure the circumference, like this. And it is about 47 inches.
Okay, so I'm going to place this balloon in the freezer, and so with a decreased temperature, the volume will also decrease of the balloon.
Okay, so now we open up the freezer. It's been about 10 minutes, and here's our balloon, nice and frosted. Okay, so I'm going to take the string, I'm going to measure the new circumference of our balloon. Keep getting it to stay on. And there we go. Okay. So this is about the new temperature of our balloon. Okay, so this is the new circumference of our balloon. Alright, so it was at 47, and now it looks to be at about 43. So this proves Charles' law.
So Amelia, can you explain mathematically what happened during the balloon experiment?
Well, Sarah. Okay, so the equation for our balloon experiment is represented in the equation volume 1 over temperature 1 is the same as volume 2 over temperature 2. Now, the room temperature of our house is 73 degrees Fahrenheit, which translates to 29.6 Kelvin. And the initial volume of our balloon was approximately half a liter. Now, we aren't positive as to what the volume of our frozen balloon was, but we know that the temperature that it was in translates to 258 Kelvin. So we are going to multiply both sides by 258 Kelvin and 258 Kelvin. So we end up with 2 liters times 258 Kelvin over 296.9 Kelvin equals our second volume. Now we cross out our kelvins. So we have 4.5. So our volume equals 0.4345 liters, and that is our volume.
Boyle's law says that volume and pressure have an inverse relationship. So that means that as volume increases, pressure decreases, and as pressure increases, volume will decrease as well. And so we're going to prove that with a syringe and a marshmallow. So I'm going to put in the marshmallow and push it so where it's not smushed too much. And so that's how many milliliters it is.
Okay, so now that we see that the volume of the marshmallow is about 2 milliliters, I'm going to put my finger over the nozzle so that no air is able to get in or out. So that keeps the amount of air that's already in there, and it stays in there. So I'm going to pull back on the syringe in order to decrease pressure on the marshmallow and increase the volume. And as we do that, Look, it is increasing as I do it. It was 2 milliliters, and now, just by moving back, it's already at 3 milliliters.
So then the inverse of that is also true. If we start with this and we push the syringe, the volume of the marshmallow changes to about 1.5. Okay, so this experiment showed Boyle's law, which says that if the pressure decreases, then the volume increases, which we showed when we covered it and put it out, and the volume of the marshmallow increased. And so when the pressure increased, then the marshmallow got smaller, and so the volume decreased.
So, Sarah, can you mathematically explain our marshmallow experiment?
Well, Amelia. So this is explaining Boyle's law. We start with the equation pressure 1 times volume 1 equals pressure 2 times volume 2. So we start and we calculated that the pressure in Austin is 1 atmosphere, so we assumed that was the original in the syringe. And then the volume we started out with was 2 milliliters, which transfers to 0.002 liters, and that's equal to the pressure for the second one that we don't know, so that's our variable. And then since it was 3 milliliters, that's 0.003 liters for when we actually pulled out the syringe. So to solve for the variable, we divide by 0.003 liters on both sides. And then that gives us our ratio of 2/3 atmospheres for the pressure that was inside when we pulled the syringe out.
We're going to prove Gay-Lussac's law, which states that P1/T1 equals P2/T2. So in other words, that means that as temperature increases, pressure also increases, or vice versa. As temperature decreases, pressure also decreases.
Okay, so now let's test this. So first, I'm going to put on my safety goggles. So we're dealing with fire. And we're going to take this hard-boiled egg, and we're going to get it into this jar. So what we're going to do is, after we set this on fire, the egg's going to go right on. Now, because we do this, the fire inside the jar is going to increase the temperature of the molecules in here, and it's going to make the pressure inside the jar a lot more than the pressure that is around it. In order to equalize the pressure inside the jar with the outside pressure, some of the gas particles will escape around the egg. But once the fire goes out with a lack of oxygen in the jar, the temperature of the molecules in here will go down, so the kinetic energy provoking them to expand will not be there anymore. It will be transferred in some other way. So with this happening, the outside pressure of the atmosphere will be a lot more than the pressure inside the jar. So the outside pressure will push the egg into the jar. And if this works, the egg will be in the jar. Okay, so I'm going to set the paper on fire. Let it burn nice and good. See if we can get a better fire than that. That's a better one. I'm going to stick it into the jar. And then I'm going to put the egg on top. And it's in!
So, Amelia, can you explain mathematically what happened in the egg experiment?
Well, Sarah, the experiment that we did with the egg can be measured through the equation of pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. Because pressure and temperature are directly related to each other. So as one decreases, the other decreases. As one increases, the other increases. So our initial pressure that we measured in Austin was about 1 atmosphere. And our room temperature measured to 296.9 Kelvin. And we're trying to find the other pressure that was in the jar while the paper was on fire. And the temperature of that was 298 Kelvin. So in order to figure out pressure, we are going to isolate it by multiplying both sides by 798 Kelvin. So when we do that, we end up with 1 atmosphere multiplied by 798 Kelvin over 296.9 Kelvin equals to our second pressure. Now when we do that, we get approximately 2.688 atmosphere. And that is our second pressure.